Okay, so I've been making some videos here that show how the central atom can change or hybridize so that it can accommodate bonding in different situations. In this case, I'm just going to go through the shapes of the hybridized orbitals, and then I'm going to do one more example of an actual molecule and how it hybridizes, and then as a result, what the shape or what the molecule actually looks like in what we call an orbital diagram. So first of all, our sample molecule for Sp3 was CH4, and what we recall here is that CH4 forms a sort of almost tripod-like shape that we call the tetrahedron. So we say this is tetrahedral. I don't know what spelling of this. And that's associated with the Sp3 hybridization. So the way that looks is one orbital up, and then these are sort of, this one might be slightly out, and this one might be slightly in, but it's sort of forming like a tripod with one of the things on top. That's a tetrahedral hybridization. For an Sp2, where we have, in here we had, right, like our 2s and our 3p's with one electron each, and they all came together to form the Sp3 new energy levels, allowing for the 4 bonds, 4 single bonds. Our Sp2 example was CH2O. Here we had 3 single bonds, so we formed our Sp2 hybridization. Then we had 1 pi bond associated with the second bond and the double bond. And we put our hydrogens here. We had our oxygen. And this molecule actually sits as a perfect triangle in the plane because the hybridization here, called trigonal planar, just looks like 3 things sitting on a plane. Now, I don't know if you've noticed this yet, but these hybridizations are essentially the shape that's associated with keeping the sigma bonds as far apart as possible. Okay, now we have our Sp associated with CH2. So let's look at what that guy looks like. So here I have carbon, carbon, and I'm going to have a hydrogen, and I'm going to have a hydrogen, and the 2 carbons are going to be bonded to each other. But for them to satisfy their octet with the number of electrons they have to work with, it'll work out to be a triple bond. So let's pick this carbon, it doesn't matter which, and look at the hybridization required to make this happen. So in its ground state configuration, it would have had a 1s2 and 2s2 electrons, and then 1 each of 2p electrons. And here we can see that it wants to form 2 sigma bonds, and then 2 pi bonds. So to make that possible, we're going to promote one of these electrons, and then we're going to hybridize 2 of the orbitals, making 2 of our sigma bonds, leaving the other 2 available as pi bonds so that we can create the second and then third double bond associated with that triple bond. So the 1s electrons are left alone again, and then my 2s electrons change into a 2sp hybridization, where those are representing my 2 sigma bonds, and then I have 2p electrons available to form the second bond in the triple bond and the third bond in the triple bond. So here I can imagine a hydrogen coming along here. Here I can imagine a carbon, and then the carbon's filling those other 2 holes as well. The hybridization shape for Sp is linear. So basically these two sigma bonds turn into a straight line. So I get a carbon, and I get the two orbitals turned into a linear thing. Hydrogen on one end, and here I'd be bonded to another carbon, which is also in the same sp2 hybridization, and there'd be a hydrogen atom hanging out on the end. And then I have 2 pi bonds to consider. So the first pi bond is pretty straightforward, because now that everything's in the plane, I can imagine a pi bond going above and below the carbon in the same plane. We show the pi bond like this, and we see the region that's associated with the possible sharing of those electrons that keeps them away from the region that's dedicated to the sigma bond, or the direct bond in between them. That represents one of our pi orbitals. Our second pi orbital, this is a little harder to imagine, but would be in and out of the plane. So these guys look like they're overlapping, but they're actually not interfering with each other at all, because one of them is in the plane and the other one is out of the plane of this actual piece of paper, and that's forming, so we have pi bond number 1, and here we have pi bond number 2, representing the orbitals that are in and out of the plane. So those are our 3 main hybridizations. Those are going to cover most of our elements. We are going to see some stuff where the d orbitals can get involved in hybridization as well, but for now, these are the main ones that I would hope that you would learn. The tetrahedral, the trigonal planar, and the linear associated with the sp hybridization, and how pi bonds and sigma bonds can be represented by, and we call this thing, by the way, an orbital diagram.